Estimating parameters and determining sample size. Section 7.2 will be estimating a population mean. The main goal of the section is to present methods for using a sample mean x bar to make an inference about the value of the corresponding population mean mu. You may use your calculator to find sample statistics for the problems in the section, x bar the sample mean and s the sample standard deviation. I've included some brief steps for calculator usage, whether you're using the TI-8384 or the 30XS Multiview. Three main concepts included in this section are the point estimate. The sample mean x bar is the best point estimate or single value estimate of the population mean mu. Confidence interval, CI. We use sample data to construct and interpret a confidence interval estimate of the true value of a population mean mu. The confidence interval is associated with a confidence level, such as 0.95 or 95%, and alpha is the complement of the confidence level. For 0.95 or 95% confidence level, alpha is 0.05. And then we'll be finding a sample size, which is the number of data points necessary to estimate a population mean. The objective and notation. The objective of this section is to construct a confidence interval used to estimate a population mean. We have three formats to represent the interval, just as we did with population proportion. We have the double inequality, lower and upper limits, but notice that it's using x bar and not p hat, and mu instead of p. We've got x bar plus or minus e, and then interval notation with the lower and upper limits included. Mu is the population mean, n is the number of sample values, x bar is the sample mean, e is the margin of error, and s is the sample standard deviation. The requirements that need to be met and the round-off rule. The sample is a simple random sample, and either of both of these conditions are satisfied. The population is normally distributed, or n is greater than 30. Unless otherwise noted, we will assume the requirements are met in the examples used in the section. Original data. When using an original set of data values, round the confidence interval limits to one more decimal place than is used for the original set of data. Summary statistics. When using the summary statistics of nx and s, round the confidence limits to the same number of decimal places used for the sample mean. Margin of error is calculated by multiplying the critical value, t sub alpha over 2, times the standard deviation divided by square root of n. df stands for degrees of freedom. In this particular section, we are using the degrees of freedom of n minus 1. You'll need that information in order to find the t critical value. Note we're using t and not z with sample statistics. The degrees of freedom we'll describe a little more in detail as we proceed. S is the sample standard deviation. It can be found using your calculator, and n is the sample size. Student t distribution. If a population has a normal distribution, then the distribution of t is a student t distribution for all samples of size n. A student t distribution is commonly referred to as a t distribution. The student t distribution is different for different sample sizes. In the figure, we have n is 3, n is 12, and a standard normal distribution curve. The student t distribution has the same general symmetric bell shape as the standard normal distribution, but has more variability with wider distributions, as we expect with small samples. Some other information about the student t distribution. Student t distribution has a mean of t equals 0, just as the standard normal distribution has a mean of z equals 0. The standard deviation of the student t distribution varies with the sample size, but it is greater than 1, unlike the standard normal distribution, which has s equals 1. As the sample size n gets larger, the student distribution gets closer to the standard normal distribution. df, degrees of freedom, finding a critical value t sub alpha over 2 requires a value for the degrees of freedom denoted df. In general, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. For the methods of this section, the number of degrees of freedom is the sample size minus 1. Degrees of freedom equals n minus 1. To find the critical value t sub alpha over 2, you need to use table A3 in the formulas and charts packet, but it has limitations. If the table does not include the exact number of degrees of freedom, you could use the closest values, or you could be conservative by using the next lower number of degrees of freedom found in the table. The upper part of the table is shown below. In the formulas and charts packet, the table is in sequence after the negative z-scores, and this is the critical t-value table. Here's an example. Find the critical value t sub alpha over 2 corresponding to a 95% confidence level given that the sample has size n equals 15. Because n equals 15, the number of degrees of freedom is n minus 1 equals 14. The 95% confidence level corresponds to alpha is 0.05. So there is an area of 0.025 in each of the two tails of the t distribution as shown in the figure below. Using table A3, to find the critical value using table A3, use the column with 0.05 for the area in two tails, which is the same column as 0.025 for the area in one tail. The number of degrees of freedom is df equals n minus 1 equals 14, and we get a t value of 2.145. Here's the picture representing what we're looking for. And if I look in the table A3, my degrees of freedom are 14. The area in two tails is 0.05. So I look in the area in two tails is 0.05. The degrees of freedom 14. And you notice right there 2.145 is my t value, my critical value t. The procedure for constructing a confidence interval for mu is as follows. Remember, we have three different ways to represent the interval. We want to verify the two requirements are satisfied. The sample is a simple random sample and the population is normally distributed or n's greater than 30. With sigma not known, as is usually the case, use n minus 1 degrees of freedom and technology or a t distribution table, we're using the table, to find the critical value t sub alpha over 2 that corresponds to the desired confidence level. We're going to find the margin of error multiplying the t critical value times s divided by the square root of n. Then we're going to use that value of e and the sample mean x bar and substitute them into one of the three formats. With an original set of data values, we want to round the limits of the interval to one more place than is used for the original set of data. But when using summary statistics, we want to round to the same number of places as the sample mean. Here's an example. Listed below are amounts of arsenic in micrograms per serving in samples of brown rice from California, based on data from the Food and Drug Administration. We'll want to calculate the margin of error for the population mean mu. Recall that the margin of error is the maximum likely amount of error when a simple random sample is used to estimate a population parameter, in this case the mean. There is probability of 1 minus alpha that the difference between x bar and mu is e or less. Calculating the margin of error, we need our formula. And this is the margin of error for population mean mu. If I look at my formula and charts packet, that's going to be on page 1, and it's the margin of error, so it's E equals, but notice there are three formulas for E equals. This has P hat in it, so that's proportion. This has a Z and a sigma. I don't know sigma. This has T and S. Let's see which one of these I need to use. So I'm going to grab both of these formulas. For E equals, I'm calculating the margin of error. and I'm going to paste them here and then choose which one I want to use. Okay, so I have, I don't have sigma, and I've got a sample that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points in it. So this one is out because I don't have sigma. This is the formula that I'm going to use, but I have to find T, and I have to find S, and N I just counted as 10. I'm going to use my TI 8384 graphing calculator to find S. I'm going to plug these numbers into list 1. So let me go ahead and do that. I'm going to go to the list. I'm going to go to Stat and Edit. That's going to provide me an opportunity to clear out list 1 and then enter my values. 5.4, 5.6, 8.4, and so on. 7.3, 4.5, 7.5, remember I have 10 data points, 1.5, 5.5, 9.1, 8.7. And then I'm going to press Stat Calc, 1var statistics, and this is going to give me S, which is 2.32487. Now we don't have the mean rounded, but we do know our original data values are to the tenths place. So S is going to be to the hundredths place. And I need my T. So T is based on the degrees of freedom. The degrees of freedom in this problem, n minus 1, is going to be 9. And I don't have a level of significance. I don't have my 95%, so we'll default to 95% confidence. Alpha is 0.05 in 2 tails. I need that. And my degrees of freedom to find my T number. In the table, I look for table A3. Table A3. And I look for the degrees of freedom as 9. And I want the area in 2 tails of 0.05. So 2.262 is my T value. 2.262. Using my calculator to plug into this formula, I end up with E equals 2.262 times S, 2.32 divided by the square root of 10, for a margin of error 2.262 times 2.32 divided by the square root of 10 is going to give me 1.6595. 1.6595. That is my margin of error. I'm not going to round to any particular place at this point because all I wanted to do was practice finding margin of error. We'll actually use the technique to construct a confidence interval in a few minutes. So we have 2 example problems. I'll work through one of them with you, and then I want you to work through the other one on your own and then compare notes. So in a study of speed dating conducted at Columbia University, male subjects were asked to rate the attractiveness of their female dates, and a sample of the results is listed below. 1 is equal to not attractive, 10 is equal to extremely attractive. Construct a 99% confidence interval estimate of the population mean attractiveness rating. What do the results tell us about the mean attractiveness rating made by the population of all adult females? So in looking for what I'm supposed to do, I'm supposed to construct a 99% confidence interval estimate of the population mean attractiveness rating. Now, because it's a confidence interval of the mean, I want to ultimately end up with X bar plus or minus E. Okay, to find X bar, I need to find the mean of the data set. So I need X bar, and then of course E is equal to T sub alpha over 2, because I don't know sigma, times S divided by the square root of N. Therefore, I need T. To find T, I need to know the degrees of freedom. I need to know alpha. I need to know S. And I need to know N. So once I find all of those parts, I'll be able to find, or I'll be able to construct the confidence interval. Using my calculator, I find that X bar is equal to 7. The S is equal to 2.2156. N is equal to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The alpha is equal to 0.01, which means alpha over 2 is going to be 0.005. The degrees of freedom are 12 minus 1 or 11, and I'm going to use the table to find T. So I'm going to look for row 11 with an alpha of 0.01 in 2 tails. Notice that in 1 tail it's 0.005. These are the same column. This is the same column for area in 1 tail and 2 tails. So I'm on row 11. 3.106. 3.106 is my T value. So taking that information, E equals T alpha over 2 times S divided by the square root of N. We found T of alpha over 2 to be 3.106. S was 2.2156. N is 12. And using the calculator to find E, 3.106 times 2.2156 divided by the square root of 12 gives me 1.9865, and I want to round this to the tenths place. So I'm going to use 2, well actually I think I'll leave it since it's E. I think I'll leave it in a long decimal form, 1.98656. And then when I add it and subtract it from X bar, that's when I will shorten it. X bar is 7, so I'm going to take 7 and add and subtract E from it to get the interval limits. Subtracting 7, I get negative 5. Oh, sorry, it's not negative. 7 minus E is going to give me 5.0 is less than mu, and then 7 plus E is going to give me 9.0. This is my confidence interval, and this is attractiveness ratings between 5 and 9. So I'm 99% confident that this interval contains the true population mean attractiveness rating. So the follow-up question is, what do the results tell us about the mean attractiveness ratings made by the population of all adult females? Well, this was a speed dating study of speed dating conducted at Columbia University, and the population of Columbia University is not of females, is not and males, is not necessarily representative of the population of all adult females. Therefore, the results really tell me nothing about the population of adult females. So that would be how I would respond to the follow-up question, is that the results tell us nothing about the population of all adult females.